Hello, welcome. Today we're going to learn about motion in a plane. We learned in chapter 2 motion along a straight line. It could be either in x-axis or y-axis. Like in free fall, it was purely in vertical direction, so that means it was only y. Or you could have a car moving in x direction. It could go forward or backward, but we never dealt with a situation in which a particle actually travels both in x and y. Okay, so this is the type of dynamics that we're going to learn about. So for example, if you throw an object like this, you can see that it will have a forward direction, so that means it has a motion in x, and also it has a vertical motion, so that means it has motion in y direction. So it's going to have both x and y component of the velocity. So to represent that, we just develop the same type of formalism that we developed in chapter 2. And let me start with a coordinate axis to understand this. So let's say that's the coordinate axis. This is x-axis, this is y-axis. And let's suppose a particle starts moving from here and maybe ends up here. Okay, something like that. And it could have a path. It could be something like that, let's say. It could be any other path. Okay, to represent the motion in 2D, we actually write two vectors. One vector is to represent this coordinate, x1 and y1, the initial position, and the final position is x2 and y2. And these two vectors are called r vectors. Okay, so r is the line that connects connects the origin to the first point, and that's r1. So let me draw that one. So let's say that's a vector, and that's r1. You can just say r. Okay, so basically the r is a vector that is formed by the x displacement, x coordinate and y coordinate. So if you look at the x, that's how much you have in x, and this is how much you have in y, right? How much vertical you have. So the magnitude is this much, and you know how to calculate the magnitude of a vector. And if this is x and this is y, we know that r is equal to square root of x squared plus y squared. So that's how you calculate the magnitude. Now to describe the motion, we want to calculate the average velocity, so how much displacement you have in certain time. And to get the displacement, we want to get from here to there. Instead of just calculating delta x and delta y, you can just get the difference in these two vectors connecting these 2 points. Okay, so let's say this is r1 now, and this is r2. So I draw this vector again. Slightly off, but so let's say that's the final point, and let's say this is r1 and this one is r2. Okay, so the difference between this vector and this vector is actually the line connecting these 2 points. So that's delta r. Okay, that's the difference in between these two vectors. So if we just calculate delta r over delta t, then we can write average velocity. So v average equal to delta r. That's the difference between these two vectors, r1 and r2, divided by delta t. Okay, so that's how we calculate the average velocity. You can actually calculate the components of these average velocities by just writing v average in x equal to delta x divided by delta t, and v average in y is equal to delta y over delta t. All right. Now we can actually calculate the instantaneous velocity. The instantaneous velocity would be the velocity, along this path. And if you get the velocity right here at this point, then it would be the slope at that point, right? If I draw that, let's say I want to get, so again, this is x and y. So if I just focus on this, curve like that. And if I draw a tangent, let's say I'm going to get the velocity at this point, then the velocity would be like this. Okay, that's v. As you can see, it has both x and y components. So if you draw coordinate axis right here, that's the angle theta, and you can write the x and y component. So basically v is equal to square root of vx squared plus vy squared, whereas where this is vx right here and this is vy right there. Okay, so that's how you can calculate the combined velocity, the magnitude, with x component squared plus y component squared, and take the square root, just like how you normally calculate the magnitude of the vector. The direction, again, tangent inverse vy over vx is going to give you the direction. So now, if the velocity itself is changing, in this case, it is actually changing. So if you have a path like this, and then you get the velocity here, the velocity is like this, and here the velocity is like that. So the velocity is changing both in direction and magnitude. In that case, you can write this as v1 and this as v2, and the difference between these two over time is going to give you the acceleration. So the definition of acceleration is a average is delta v divided by delta t, right? And that's the vector. So this is how you calculate. And you can calculate the acceleration at any point by just writing the magnitude as ax squared, which is the x component of the acceleration, plus y component of the acceleration, ay squared. And this is all. I mean, these are the different ways of writing the total velocity and acceleration. And we'll deal with different motion, like projectile motion or motion along a circle. And these type of problems will have both x component and y component. Okay, so if you're given a velocity like this, you just need to get, let's say you have a velocity vector, any one of these vectors, okay? And then the angle is also given, and that's the v. And you can just get the x component, which is here, right? That's vx equal to v cosine theta. And this is vy, and vy is v sine theta. And you have vx and vy, and you can calculate the total velocity. That's all, right?